Hello, everyone. I'm going to be going over our review worksheet that I handed out. This one was very similar to the test itself, so hopefully if you do well on this or you think you have what's going on, then we should do fine on the quest that we have. So without further ado, let's begin. So this first question is a fairly simple question using A is equal to F net over M. However, the a little complicated bit is you actually have to do the same equation twice. Our first goal is to figure out the mass of the object, and our second goal is to use that mass to find the force that's needed. So I'm just going to plug in my values of 5 is equal to 10 divided by our mass, and we should get a mass of 2 kilograms. And now with our 1 meters per second squared and our 2 kilograms, if you do the math on that, we should get 2 newtons as our answer. Hopefully that makes sense. All right, this one over here seems like a gravity question, but it's really not. This is, and they're always hiding in plain sight, this one is our Newton's third law question. So we have Earth on Moon and Moon on Earth. Once you see that switching of the nouns, that should trigger something in your brain to say, hey, this is a Newton's third law question. It's the same. So the force of the Earth on the Moon is F, so that must mean the Moon on the Earth is also F. Now, of course, the Moon moves a whole lot more than the Earth does, and the difference, they have the same force, the difference between them is their mass. All right, question 3 is a circular motion question. Sorry for not heading the 1, 2, 3, 4 for it. The real only trick here is the fact that they're asking for acceleration. They're not asking for the force. So you don't need this 0.4 kilograms. That would only be important if you're looking for the force of the object. All right, one quick thing. I don't think I put in one. Okay, I do have one. Sorry, my apologies. Okay, so sorry, back to that. So we're just using the simple formula of A is equal to V squared over R, where our V squared is 4, so 16 over our 0.8 meters. And if we do that, we should get 20 meters per second squared. Our next one is another one using our Newton's second law. A is equal to F net over M. This one has the added trick that we need to find the net force. We see it's 8 to the left, 3 to the right, so our net force is 5 newtons to the left, which means our overall answer is going to be to the left. So right away, I know it's going to be 2 and 4. Divided by our mass of 2 kilograms makes it 2.5 meters per second to the left. Next one is our gravitational question. So a lot of the times this is used to convert mass and weight. However, in this case, it's used to, do that conversion but of a different planet. So G is not going to be 9.81 like it would be on Earth. Instead, it's going to be the 16 value. So it's going to be 16 is equal to Fg over M, where M is the 6. So it's just going to be 6 times 16, which is are 96. All right, I do like this question a lot, though it is simple. So which diagram represents the force exerted by the table is the key thing. So the table is pushing up on the block. So right away, I know it's not 4 and not 2 because the table is holding the block up. Now, the key thing is we're looking for force here. So right away, we should be thinking of newtons, and it is, in fact, the 49.1 newtons. Now, where did that 49 come from? That is this formula again. Though this time we are using 9.81, and we're simply converting between our weight and our mass. So we have 5 kilograms, and we're looking for our weight on the top, which we get the 49.1 newtons, and that is how much the table holds it up. Kilograms is not a force, that is a unit for mass, and something can't push something by a certain amount of kilograms. It doesn't make any sense because kilograms is how much stuff something has. Greatest inertia, again, inertia, mentally I cross out inertia and I write mass. And so what one has the highest mass looks like it would be the seated high school student. All right, here we have a friction question. That's what we're thinking about. Sand is often placed on a road because we want to increase the friction so we don't slide off. Obviously, we can't change the gravity of the car using sand. That would be pretty cool. It's not increasing the normal force of it. Instead, it's increasing the coefficient of friction. That makes it the tires stick on the road more rather than slide off. All right, here's our gravity question. Don't forget to square the r. This one's a pretty straightforward one because we have a small number. So again, g is 6.67 times 10 to the minus 11 times our masses, which is 7 kilograms, times 7 kilograms, divided by my r squared, which is 2 meters squared. And when you do all the math out, I believe you get choice 3. All right, so next one is one of the pointing, or which direction is it pointing. We're looking for the centripetal. Centripetal, again, means center pointing, so it's going to be pointing towards C. Now, I do want to go over one other type of question that we might see that's like this, which is, what if this toy was cut? Like, what if this wire broke off, or the mass went flying on its own? Which direction would it go? And it goes in the direction of its velocity, which is always tangent to the circle. So if the wire was cut, it would move to D, but the centripetal force and the centripetal acceleration are pointed towards C. All right, now we have some Part C questions and some ramp practice that I added on to the end. So for question 11, what is the net force acting on the box? So people's first look is think of the forces that are on the box. We have the 15 newtons, and we obviously have friction. And by the fact that they're asking me to find the friction means I probably can't find it the other way. And yeah, because I don't know the materials of the box, there's no way I can find friction to find the net force. So we have to do it our secondary way, which is using Newton's second law. I know my acceleration is 2. My net force is what I'm looking for. And my mass is 2.5, which means my net force is 5 newtons. All right, and again, as we go to 2, our first thing, we see force of friction. Most of the time, we immediately think of this formula. However, again, there's no way for us to know what mu is in this problem. So this is not the go-to formula. Another hint to that is the fact that it's a one-point question, which means you're probably not going to use a formula. Not all the time, but probably. And we're not in this case. Instead, we're going to use our other definition of what a net force is. F net is equal to the sum of the forces, and it's the vector sum. So because I have 5 newtons is equal to our force plus our force of friction, and we know that force, I'm sorry, I'm writing it all over the place, is 15 newtons. That must mean our force of friction is -10 to be able to solve this problem. So -10, or just simply, because it's asking for the magnitude, so not direction, 10 newtons is my overall answer. We got a ramp question. Again, for these, I like drawing the arrow straight down through the ramp, and that connects back up to the ramp, so it makes a 90-degree angle. This angle right here is 15 degrees. 8 newtons is my gravitational force going down, because again, weight is the same as force of gravity. And so this is just a sine, cosine, tan. What is the net force causing the block to accelerate? That is this, oops, sorry about that. That is this side of the triangle. This side over here is is equal to the normal force, and they cancel each other out. So it's this side at the top, if we're frictionless, which we are, is equal to the force that's causing our acceleration. So this is going to be sine, because it's opposite of 15, is equal to what we're looking for over our 8 newtons. And if we do the math for this out, we get 2.07 newtons. And we should see that's much smaller than 8 because it's sine of 15, which is a fairly small number. All right, here's another kind of force at an angle type of question. So again, I'm going to break this up into its two parts. This is just a vector resolution. And our goal is to find the horizontal part. So it's just going to be cos, because we're looking for the horizontal of 30, is equal to x over 60. And then if we do the math for that out, we get 51.9 newtons. So pretty big. Determine the force of friction. Now again, we're like, okay, is this skis on snow because it's sled? No, it doesn't say that anywhere. So again, our first look, because we see force of friction, should probably be this formula. However, again, there's just no way for us to, we don't even know what the normal force is. There's just no way for us to use this formula to get this answer. But what we do know, and what I see over here, is the fact that it's moving at constant velocity. That means that my force going one way has to equal the force going the other. So again, it's the 51.9 newtons a second time, because they have to cancel each other out to be going at constant velocity. Now the reason why I put these last couple in here, friction and this formula, this force of friction formula, is fair game for the quest. However, I wanted to show you some cases where that formula is not used. Using that formula, very straightforward. Just check your reference table, look for the appropriate mu, and then solve the problem. But sometimes you don't need to do that, and that's what I was trying to point out with these two questions in this example. All right, that is everything I have for today. If you have any additional questions with this, please make sure you let me know before you're actually taking the quest itself tomorrow in class. Have a good one, everyone.